All right, good morning, everybody. My name is Ryan Clementson.
I'm Chris Popper.
And we'll be presenting today another ToloTalk webinar. Thank you for joining us on sizing electric actuators for successful displacement or replacement of hydraulics. So what are we going to talk about today? There's a lot of reasons that people use hydraulics and are going to continue to use hydraulics. They've been in place for hundreds of years effectively, and over the last 20, 30 years, electromechanical actuators have made significant advancements in longevity, ease of integration, reliability, performance, and so there are machines, processes, and places where maybe you've got a new machine or there's an existing machine that maybe just needs a little bit of a refresh. And electromechanical solutions are becoming a very viable option. And some of the reasons that we're seeing why people are replacing the hydraulic cylinders in existing machines would be for an improvement in performance, whether that's in part quality, total cost of ownership, whether that's from tooling costs, part rejects, utility costs. There's a lot of additional maintenance that can go into hydraulics, whether that's from filters, oil replacements, valve adjustments, cylinder rebuilds. There is maintenance intensive work that is required on hydraulics. You could have simpler installations. Again, fewer components typically, where you don't have the power unit, hoses, filters, not regulators, but relief valves, flow controls, all of that. With electric, you've got fewer components that you need to put in place. And again, kind of just circling back around it, there's a lot of maintenance that goes into hydraulics, and we're not trying to ignore that fact. And so we have a lot of resources on our website, so I would recommend that you go to that. We've set up a URL, tolomatic.com/hydraulic conversion, and we'll talk a little bit more about what that content is on the page here in the presentation. So when you're getting started and you say, I've got a cylinder and I want to replace it with an electromechanical, what do I need to do? You need to know how much force you have. And so the first formula that you're going to go to is force equals area times pressure. And so we're going to talk about that. We'll go through a couple of different ways that you could take some of the force measurements, and we'll use our little trainer here to demonstrate that and talk through why it's important to be as accurate as you can in understanding your requirements. And so, like I say, we've got our trainer here where we've got a little valve, we've got a power unit down below, we've got a cylinder that's being powered by the power unit, and then we've set up a secondary cylinder here with a couple of needle valves so that we can create resistance and simulate different loads. And then we've got quick disconnects located all over it here. We've got a couple of gauges that will read some pressures where we'll have a pressure on the piston side or blind side that's going to be seeing a resistance from here. And then we will also be seeing a resistance on this cylinder right here for simulating back pressure. And so we want to, take into account that every hydraulic cylinder or circuit is going to be a little different. Sometimes you may see high back pressure in return lines. Other times you may see low back pressure in your return lines, and that does have an impact on the actual force output of the cylinder. So we'll use this today for that. And in a real world situation or in a machine that you may be working on or looking at, measuring the pressures is important. That's a function of the work being done. And depending on the installation and how the machine is deployed, you may not have access to the best place to get pressures, or even many different places to get pressures read. So from our standpoint, a good place is right at the valve. And so you're going to have your outlet line, you're going to have your return line. And so if you can get gauges on the valve, that's pretty good. It might, in many cases, be the most practical. A better place is going to be somewhere in between. I've got a squid of hoses back here, but in your situation, you may have a longer run of hose, you may have a pressure reducing valve, flow meters, flow controls, any sort of break in the lines where you could get an additional gauge and just get closer to the true point of work. That's going to be better. Your best place is really going to be right at the point of work here. And so that's what we've done with these two gauges, where I put a T in and then we run gauges back out. And so we're going to measure right at the point of work of the cylinder. And this may, in many cases, be the hardest place to get access to, because they're remote mounted versus the power unit or the valve might be in a place that's more easily accessible. So do the best you can, and just know that the closer you get to the point of work, that's going to be the most accurate place to measure. And so we're going to fire this up, and I'll apologize about the power unit noise. It gets a little bit of a hum, just like all power units do. But we're going to look at 3 different ways of calculating force using pressure. All right, so we'll use one, which is your system pressure. And this is one that we see most commonly in applications where they're looking to convert, where it's my relief valve is set to 1500 PSI. My bore is 1.5 inches in diameter. I'm going to take area times pressure, and that's my force. So we'll talk about that. We're going to do one where we call it pressure differential, where, similar to the graphic on the screen here, we're going to say, all right, well, I've got, in this instance, 150 and 450. I'll subtract the 2, so my working pressure is 300. We see that oftentimes. And then we'll do a third one here where it's really more talking about the effective surface area of the cylinder. So what is the pressure and how is it affecting on the surface area on each side of the piston, whether it's the rod end or the piston end. So with that, we're going to fire this up, and we'll take a look at a couple of different pressures on the circuit. And so I'm going to be extending. If you take a look right here on the screen, you'll see the clevis moving back and forth. So I'm going to extend. And then right here is going to be your piston end or blind end pressure. Right here is going to be your back pressure. So I'm going to start with a retract move. I'll do an extend move. Let's do it a couple more times here so you can see the pressures. A little bit of a jump from the relief valve. All right. It was a little bit hard to see, but for those of you that weren't able to see, what we had is on the blind end during extend, we had about 450 PSI. On the back pressure side, on the rod side, we had about 170 PSI. So we're going to use those, and we'll flip back to the slide and we'll talk through the 3 different methods for calculating the outputs. So as I mentioned briefly, we've got a 1.5 inch bore. Okay, we got a 3/4 inch rod. We had 450 PSI. Extend. We had 170 PSI on retract. And we'll just say that our system pressure is 1500, because that's what it is. Rating, not relief valve. So I'll just put that up there too. So if we use the system pressure method, we're going to take our 1.5 inch bore and we're going to multiply it by 1500 PSI. So we're going to have an effective surface area of 1.767 inches. And then we're going to multiply that by 1500 PSI. And that's going to give us about 2,650 pounds of force. Okay, so that's assuming the system pressure. Now, if we take the differential method, where I've got 450 PSI minus 170 PSI that we showed on the gauges for an effective pressure of 280 PSI, if I take 280 times 1.767, that gives me about 500 pounds of force, about 495 pounds of force, roughly. Okay, so that shows a pretty significant difference from the system pressure. So if we're going to say, at first I thought it was 2,650 pounds. Well, just by getting a couple of simple pressure measurements off the cylinder, now you've taken a very significant force requirement out, which is going to minimize cost, minimize envelope, minimize a lot of different pieces, panel space. So you're seeing a big benefit to accuracy by just getting those measurements. So now we'll go to the effective area method. So we know I've got 1.767. That is my rod or my piston diameter. If I take pi r squared times 3/4 of an inch, that's going to give me 0.44 inches. I'll just put that there. So if I subtract those, actually not multiply, my apologies, I'm going to get about 1.327. Okay, and the reason that's important is I'm going to take that area, the 1.327, and I'm going to multiply it by my back pressure of 170 psi, and that's going to give me the amount of force that the blind end is having to overcome to move the load. So if I take 1.327 and I multiply that out by 170 psi, that gives me 280 pounds of canceling force, so to speak. All right. And then if I take 450 psi by 1.767, that's going to give me 795 pounds of force. So I've got, actually it's 225, sorry, not 280. Correct myself on that, make it accurate. So if I take 795 minus 225, I get 570 pounds of force. So you can see conservative measurements get you close, but getting accurate measurements is going to get you where you need to be so that you're not potentially undersizing motors, undersizing actuators, misunderstanding what your life expectations might be. And as we move on to the next slide, we'll give you a little bit more of a representation here. So this is not indicative of the numbers that we put up here today from the trainer, but in the event that you got up a number of 850 pounds by whatever method that happens to be, you could potentially spend upwards of $2,000 on just an actuator, not counting motors and drives. But if you do a more accurate measurement assessment over your pressures and forces by the methods that we've shown you here today, you could potentially save 50% on just the actuator cost alone. And so even having a variation of a couple hundred pounds of force, though it doesn't feel like it's significant, when it comes to electric actuators, it actually is very substantial. And this gets more and more pronounced as you get to bigger actuators. And so we just wanted to get that in front of you and let you know that this is why it's very important to be accurate in your assessment of your forces in your hydraulic circuits. So with all of this, you know, we're not telling you have to be experts. You know, there's probably many of you out there today that are, and that's great. But for those of you that this is kind of your first foray into electric actuators or dealing with hydraulics and trying to convert them over, we have the people, we have the resources, and we have the expertise to be able to support these activities, whether that's in our sizing software, our application worksheets, our education resource pages. So we want to let you know too that we have the ability to work with you to solve these solutions. And so, as I mentioned in the beginning, you know, the tolomatic.com/hydraulic conversion, that's got a lot of resources. As you can see here, it's got a full video of what we've done today with this trainer. And, you know, certainly make sure to go take a look at that. We've got application engineers here at ToloMatic. We have regional area managers all over the world that are able to also be a local resource and assist you and support you. So certainly check out that set of resources and let us know how we can help.